This is the screen recording for the Solving Systems by Linear Combination notes. Okay, the previous day we had learned to solve systems by substitution. We had done earlier solving it by graphing. And these are all different methods to accomplish the same goal, to find the one point, the combination of x and y, that make two equations true, where they intersect, the one that works for both of them. I have the written out directions here. This one, some of you can see it, could lend itself pretty easily to substitution, but we're going to use the other method for now. Linear combination comes into play nicely if you have to solve for a variable, it gets a little messy. So you need to be kind of flexible about when you use either one. You do need to know both. I will assess that you know both methods. So I'm going to look at the two equations, pick a variable, x or y, it doesn't matter. And you can see from this problem, I chose x, that I was going to add to be 0. So I looked at 5 and 2, the coefficients in front of x, and tried to find the least common multiple, or the smallest number that 5 and 2 can both divide into, and that is 10. Now, if I want them to add to be 0, I'm going to need them to have opposite signs. I need one to be positive 10 and one to be negative 10. So you can multiply the entire equation. So if you take the top equation, I'm going to multiply the entire thing by 2. The reason for that is I'm trying to make the coefficient in front of x to be positive 10. We saw in class that when you graph these in Desmos, it is exactly the same line. Multiplying the entire equation by 2 does not fundamentally change the equation. In the bottom equation, I multiplied that by negative 5, again with the goal of making the coefficient in front of x in the bottom equation to be negative 10. You can see I multiplied all of it. Make sure to multiply every part of it. I added down the columns. 10x plus negative 10x is 0. 6 plus 20y is 26y. 18 plus negative 200 is negative 182. And I got y equals negative 7. I showed that over here as well as I started to go through the directions. So that's my y-coordinate. So that's nice that I have my y-coordinate, but I need to know the x-coordinate of this intersection point. So I took the negative 7 and I plugged it into one of the original equations, and I solved for x, so I got 6. And then I needed to check. So my original equations were 5x plus 3y equals 9. I plugged in 6 for x, negative 7 for y, and then I simplified it to see if the equation stayed balanced, and it did. 30 minus 21 does equal 9. Then I did the same thing into the second equation, which was 2x minus 4y equals 40. I plugged in 6 for x and negative 7 for y. I simplified again. If this point is on the line, then the equation will be balanced. The left and right side will be equal to the same thing, and you see that is here. So that is a way you can check your answers. Over here, I did another one. Again, it's your choice what you want to cancel. You can cancel x or y. I again chose x, just personal preference. In this one, a lot of people will just say, oh, just add down because they already add to be 0. They don't. It is very important, the sign of the number. 4 plus 4 is 8, not 0. So I had to multiply the bottom equation by a negative 1. So I multiplied all of that by a negative 1, and then I added 4 plus negative 4 is 0. Okay, that's good. 9y plus negative 3y is 6y, and so on. I got my value for y. I plugged that back into an equation into one of my top equations. I plugged 7 in for y to solve for x, and I got the intersection point is 3, 7. You can check this as well. You can put it into Desmos, or you can plug them into each equation. Remember to do it to both to make sure it works for both. In the next two examples, what I would like you to do is try these by yourself. Even if you can only get through a couple steps and then you're not sure what to do, at least you put some thought into it and your brain will learn it a little better than just hearing me talk about it. So try these, push pause now. All right, over here in the top, I decided to have the y's add to be 0 this time, change it up a little bit. Now you'll notice in this one, I didn't multiply by opposite signs. I had some people in class when we did this say, oh, do you always have to multiply one by a positive and one by a negative? Not necessarily. When I was looking to add to make the y's add to be 0, I already saw they had the opposite signs. So I'm going to multiply both of them by a positive number. Again, I looked for 3 and 5 and said, what's the least common multiple of 3 and 5? That's 15. So to get this to be 15, I had to multiply the entire equation by 5, and that'll give me a negative 15 in the front of the y. And to get a 15 here, I had to multiply the entire equation by 3. Add down the columns, solve for x, take the x, plug it back into one of the original equations, and solve for y. So my answer is negative 1, 2. In the second equation, I did the same thing. This time I looked for the x's to add to be 0. Since the coefficient in front of x here is positive 1, I multiplied this by negative 1, and I added down the columns. I solved for y. I took my y, I plugged it back in to one of the original equations, and solved to get the x value, 11, negative 3. Again, on this slide, I would prefer if you would push pause, try them yourself. Maybe you could only get halfway through the last time, but you can get through a little more this time. So please push pause and try these on your own. All right, in the first example, I decided to have the x's add to be 0. So I looked for the number that the least common multiple of 3 and 2, that is 6. So to get this coefficient to be 6, I have to multiply the entire equation by 2. To get the bottom equation to be coefficient to be negative 6, I multiplied the entire by negative 3. I solved for y, I plugged it in to get my x, and there's my answer. And again, I think you can see that here. If I move too quickly or you need to check your work, you're welcome to push pause at any time. But at least you have that here. And again, you can always check them by taking the x and y coordinates, plugging them in for x and y into each equation, and making sure that your left side and your right side both equal the same thing. So that is solving systems by